Hey everyone. Today we're going to be learning about a few different types of wave phenomena and exactly how these contribute to our understanding of waves and how they're going to interact with each other. We first need to understand what a wave front is, and we kind of see this represented here in the image with the ambulance. And a wave front is the locus of all adjacent points on a wave that are in phase. And really, what that's saying is all points on this wave here, in front of this ambulance or behind it, are all constituting a wave front of this particular wave of the sound of the ambulance. And to show you what this means, I'm going to show you this in two different views. If we drop a drop of water out of this faucet, we're going to see two wave fronts here spreading away. And I'm going to leave this on so we can kind of watch this. But we're going to have crests in the blue here and troughs in the black line here. But all points on this blue semicircular front is considered a wave front. And they're all, the blue line from the black line, are separated by one wavelength. And these blue lines here that are radiating from this source here of dropping water are considered in phase with each other. If we look at this from the side view, we've all probably seen this before, water dripping into a container of water, and we produce these wave fronts moving from left to right. And this wave here and this wave here are considered in phase with each other. And we'll come back to this momentarily. So any point there on that line is considered a wave front. Now, the Doppler effect, you're probably more familiar with this than you think. But the Doppler effect is a change in observed or apparent frequency of a light or sound wave due to the relative motion of the source and the observer. Now, I'll give you a couple examples of where we actually use this. We use this a lot in weather forecasting. Sometimes you'll see that on the broadcast it says Doppler radar. It would be using this phenomena of waves, which we'll talk about in a second. And another example is police work with radar guns. So the Doppler effect, and the example I'm going to use is a moving ambulance. This is probably where we most often have a interaction with this phenomena. And the Doppler effect says that if we have a source, in this case a source of sound that is moving, the sound waves are going to bunch up in front of the moving object that's creating sound, which is going to change the wave's frequency. So if we're standing in front of a moving ambulance that's maybe going, I don't know, let's say it's moving 40 miles per hour down the road. We're standing down the road and we can hear the ambulance coming. We're going to hear a higher frequency of that siren because these wavelengths are bunched up in front of the moving object that's creating the sound. Behind the object, we can see the sound waves are spread apart farther than they normally would be, and we're going to interpret that as a lower frequency. So if we were standing, let's say where this guy is at point 1, we're going to hear a high frequency of sound as the ambulance comes towards us, and as it passes, we're going to hear this lower frequency of sound, and that's why an ambulance or anything that's moving, it can be a car just driving down the road, the sound of the tires on the pavement, it's going to have one sound as it's coming towards you because we have this higher frequency from the sound waves being bunched, and when it passes, we see this spreading of sound waves behind the object as it passes. We'd hear that as a lower frequency from whatever the object is that's creating sound. It could be a barking dog, anything that is creating sound or light, or any type of wave that is in motion. Now, interference, we see a lot of this. This is a pretty heavily tested topic on your Regents, wave interference. We'll spend a little time talking about this. But if you guys have questions on any of this, I did include a video for you to watch this week on this as well. If you have questions on any of this, make sure you reach out and get your questions answered. So we're going to start with superposition. Superposition occurs when two or more waves are going to travel through the same medium. Remember, a medium is a matter of, or a body of matter, simultaneously. So if we have one wave moving, I'm going to pull this up here. If we have one wave moving through an opening here, and let's say we were to do two openings here, we're going to have different wave fronts that come through these openings, and they're going to interact with each other. So you kind of think of it as maybe in a classroom, if you have two doors here, if you were to stand in the middle back here between this barrier, you're going to get different sounds that come through each of these openings, and it's going to cause the sound that you hear here to be different than if you were standing in front of this barrier. So the principle of superposition states that the resultant displacement at any point is the algebraic sum of the displacements of the individual waves. Now, the effect of superposition is called interference, which can either be constructive or destructive. And basically what this means is that when waves combine with each other, they're going to affect each other in some way, and they're either going to combine in a positive way or combine in a negative way to adjust the frequency of the wave. It's also going to adjust the amplitude of the wave depending on how they're going to interact. So in constructive interference, that occurs when the wave displacements of two in-phase waves, so they're not separated by any they're not out of phase at all by any type of degree. They're completely in phase. Their degree of separation is 0 degrees. So the two in-phase waves in the same medium, and they're traveling in the same direction. If these are being met, then we can have constructive interference. And we'll take a look at an example of this in a second. Now, the point of maximum displacement of a medium when two waves are interacting is what we call an antinode. And that's when the phase difference is 0 degrees. And what this is going to do is it's going to cause our amplitude of our wave to basically increase. As long as the phase difference is 0 degrees, and these waves are traveling in the same medium in the same direction. Now, destructive interference is going to be the opposite of constructive interference. Now, this is the effect produced when two waves of equal frequency and amplitude whose phase difference is 180 degrees meet at a point. So the phase difference is 180 degrees, which will mean maximum destructive interference, and that's going to result in the formation of nodes. which can be points or lines. And these are regions of zero displacement of the medium. And we can have intermediate degrees of interference here as well between these two maximums of 0 degrees phase difference and 180 degrees phase difference. So to see an example of this, we have two waves here, the red one and the blue one. And we can see the crest of the red one lines up with the trough of the blue one. Now this would be, as we can see here, destructive interference. These two waves are 180 degrees out of phase. A crest is lining up with the trough. So we could call this, let's say, negative 0.75 and a positive 1. The difference, or the sum, if we add positive 1 plus a minus 0.75 would give us a positive 0.25, which is, this is the resultant wave that we see here. So it's the combined effect of this red and blue wave is the black wave here. And depending on how the red and blue line up, let's say the crest with the red lined up with the crest of the blue, these amplitudes would, again, this is the sum, these would combine and we'd have a much taller amplitude, maybe something kind of like this. And that would be crest and trough. That would be constructive interference. And we see that over here as well. Two waves here, trough lining up with trough and crest lining up with crest. These two will combine. We have the sums of the crests and the troughs that combine into a resultant wave. And we see the amplitude of this wave is the combined amplitude of these two waves. But the frequency of these two remains the same. In destructive interference, if we have 180 degrees out of phase, our resultant wave is essentially canceled out. And we're left with no wave there. Now interference, I'm going to actually start this with, no, we'll do it with the two slits here. If we generate waves from this wave generator, I can't really, I guess I can pause that. These two waves, separated by a wavelength here, it looks like about 1 centimeter, they're going to meet this barrier, and we're going to talk about diffraction in a second. But these waves are going to come through these slits here. We'll see that. And we see two new wave fronts that are coming through. Now these two wave fronts are the same, they're the same frequency, they're traveling in the same medium. These two waves are going to be able to combine with each other. In this case, this would be constructive interference. When we play this here, we see where our wave crests combine with each other in the middle here. It's a little tough to see. We would have constructive interference because these are in phase waves. So the two wave fronts here, the semicircular wave fronts, are combining with each other at these points to create a resultant wave that is going to have a higher amplitude than the wave that we started with. The dark lines here are going to be our troughs of our wave. And where they combine with each other, again, traveling in the same direction, the same medium, and they're 0 degrees out of phase, we have maximum constructive interference with the wave here. And we can see that this point here where they are interfering has a greater amplitude than what we see at the edges of the wavefront. And this is our effect of interference, and we see that right in the middle here, where these two semicircular wavefronts are combining with each other, crest to trough, increasing amplitude, remaining the same frequency, and this is demonstrating interference. Well, a standing wave, another phenomena that we're going to learn about, is a pattern of wave crests and troughs that remain stationary in a medium. A standing wave is going to be formed when two waves that have the same amplitude and frequency are going to travel in opposite directions through a uniform medium. Now the nodes and antinodes are going to remain stationary, and that's going to cause the wave to appear to stand still. It is moving, but it's looking like it's standing still because we have these waves with the same amplitude and same frequency, but moving in opposite directions. And the key here is that the nodes and the antinodes are going to look like they are not moving at all. And it'll kind of look just like we see a wave kind of standing there. And if we think of the wave moving in the other direction, maybe this one's moving in that direction, we'll do one moving in this direction. And what it's going to do, it's going to be kind of hard for me to draw. Get it like that. That lines up pretty good. What we're going to get here are antinodes and nodes. And these points are going to look like they're remaining stationary. But because of these waves moving with the same amplitude and frequency in opposite directions, that's going to cause them to look like they're remaining stationary, even though both waves are moving in opposite directions. Now, resonance, you might be a little familiar with resonance. And every elastic body has a particular frequency, which we call its natural frequency. What this means is that when a periodic force is applied to some elastic body, it's going to absorb energy, and the amplitude of its vibrations is going to increase. So we're going to see some interference here, constructive interference. It's going to cause the amplitude of vibrations to increase. And this amplitude can continue and continue and continue until it gets very, very great, which can have different effects on the body depending what it is. Now, resonance is the vibration of a body at its natural frequency because of the action of a vibrating source of the same frequency. Now, an example of this that you might have heard about before is where an opera singer can shatter a piece of glass. Now, the opera singer can produce a wave or a note that has the same frequency as the natural frequency of the glass. We can have constructive interference where the amplitude of these waves are going to increase and increase and increase to the point where the glass will eventually shatter because it can't contain the energy of the vibration of the matter in the glass. I always thought that was kind of neat. Now, diffraction, the last phenomena that we'll talk about, is the spreading of waves into the region behind a barrier that's in the wave's path. The parallel water wave fronts incident on a small opening are diffracted to form concentric semicircular fronts. And we looked at this in the simulator a few minutes ago. So with a single slit, if we have waves coming towards a barrier with a single slit in it, we see that the waves spread out in this semicircular pattern beyond the barrier. If we change the slit from a narrow to a broad opening, we see that the formation of the waves beyond the barrier are different depending on the size of this opening. Now, depending on the size of the barrier, If the barrier is longer than the wavelength, we'll get this region behind the barrier where we're not going to see, hear, or be able to interact with the wave that is moving past the barrier. We get this region of kind of dead space here. Now, if this barrier was longer than the wavelength of a wave of sound, we would essentially not hear anything at all right here behind the barrier. Well, it doesn't usually happen very often because we don't have a barrier that's longer than the wavelength of a wave of sound necessarily, but it is certainly possible. So in order that this was a sound wave, in order to hear this, you'd have to stand kind of back here where we'd be interacting with the wave fronts a little bit more. Now, wave interference, we were looking at this with the simulator. With two openings here, we have the same waves moving through the slits here, and where we have crests combining with each other, something like that, and like that, we can have maximum constructive interference. So if you imagine if you were standing here, if this was sound coming through here, you're going to hear things a lot differently than if you were standing in front of the barrier here. And it's not only because of the diffraction of the sound waves between the slits, but because of the interference of the waves coming through here. So depending how you're hearing these crests and troughs, they could be combining constructively or destructively to change the waves of sound that we're hearing beyond the barrier. Now, these are kind of just simple explanations of all these different types of phenomena. I'm going to give you guys a chance to work with these pretty extensively. But this is really the heart of this particular unit on waves. So as you guys are working through your assignments, make sure you generate a list of questions and make sure you ask those and get some answers to your questions. Hope everyone has a great day.